In Chapter 7, it's going to look very, very similar to Chapter 6, except instead of making inferences for categorical data, we're now going to be making inferences for quantitative data, specifically means. So we're going to start off in Section 1 talking about creating a confidence interval for a mean. The best way to kind of do this is through an example. So we have that a farmer wants to estimate the mean weight in grams of all tomatoes grown on his farm. To do so, he selected a random sample of 4 tomatoes and calculated the mean weight in grams to be 110. Assuming the population of all the tomatoes in his field is normally distributed, use the sample mean to create a 99% confidence interval for the population mean. Suppose the standard deviation from his tomato field in the past has been 40 grams. So to start off this problem, we want to figure out what we're trying to find, and we'll go ahead and calculate our critical value. So our mean here is going to represent the mean weight of tomatoes. And in order to calculate my critical value, I go to INV norm, half, so 99%, the remaining percent would be 1, half of that is 0.5%, so my area is 0.005, and we're going to get 2.58. So the next thing we want to do is go ahead and check our conditions. So just to refresh, so for random, we're looking for either to say SRS or random sample, and in this case, it does say that he selected a random sample. Right, then we'll check independent, so 4 has to be less than or equal to 0.10 of all tomatoes, and we'll just go ahead and assume he plants at least 40 tomatoes. And then lastly, for normal. So now, obviously our sample size of 4 is not greater than or equal to 30, but it does say in the problem that the population is normally distributed. So we're good. So because remember, no matter the sample size, if your population is normally distributed, your sample will as well. So now we can actually go to construct our confidence interval. So just to kind of refresh our memory, the very basic definition of a confidence interval is the statistic plus or minus the critical value times the standard deviation. And the critical value times the standard deviation is where we get our margin of error. So for means, our statistic is represented by x bar plus or minus. Our critical value is still the z asterisk. And then if you remember from chapter 5, the formula for standard deviation is standard deviation over the square root of n. So that's how we get our formula for the confidence interval for a mean. So now my x bar is 110 plus or minus the critical value we calculated, 2.58, times our standard deviation, 40 over the square root of 4. So when I do 2.58 times 40 over the square root of 4, we're going to get 51.6. So we have 110 plus or minus 51.6. So when I add and subtract that from 110, we get 58.4 to 161.6 for our confidence interval. And lastly, we'll do our sentence. So we are 99% confident that the true mean weight of tomatoes is between. Now with means, when you write your sentence, you do need to include units in your sentence. Because when we did proportions, since those were percentages, we left it as a decimal. They don't have units. But here we're going to have units. So it's 58.4 grams and 161.6 grams. So what we just did is called a one sample Z interval for meats. So just like we had a one sample Z interval for proportions, now we have one for meats. So what we just did, example-wise for our confidence interval, and when we were talking about in chapter 5, we were working with distributions where we knew the population standard deviation, which is not going to be the case. Most of the time, we'll have our statistic, our sample mean, and we'll have a sample standard deviation. So instead of it being a test statistic with Z, we now have a new test statistic, and it's called a T statistic, and it has its own distribution associated with it. So it's not exactly like the standard normal curve, but it's very, very close. So a couple things that are still the same. It's still centered at 0, and it is still bell-shaped, just like the normal curve. But the spread is going to be slightly greater than the standard normal distribution. Not enough that it causes a significant difference in the shape, but just slightly bigger. And it's going to have more area in the tails, which are the ends that go towards infinity and negative infinity. So when we have our T distribution, it is going to be dependent on the sample size, which will be used to find our standard deviation of our sample. So the dependence on sample size is taken care of via something called degrees of freedom, which we denote with DF, and degrees of freedom are just your sample size minus 1. So it's going to be a very, very important concept for a lot of what we do in Chapter 7 is degrees of freedom. So what we have next here is just basically a summary of everything. So density curve of the T distribution, similar to the standard normal curve, still symmetric about 0, still bell-shaped with a single peak. But the spread is a bit greater, and that's because you're using your sample standard deviation for a fixed parameter, which introduces more variation. And then as your degrees of freedom increase, the density curve actually gets closer to the standard normal curve. So we'll just give a short little kind of example of this. So we'll have so let this one be our normal curve. Okay, centered about our mean 0. If we have a small n, then we'll have a larger tail with a smaller peak. So this is for a T distribution where n is small. But as n gets larger, the tail kind of gets closer to that of the normal curve. The peak gets a little bit taller as well. So then we have our T distribution where n is large. So just like when we were doing sampling distributions, we wanted a large sample size to reduce variability. When we're doing confidence intervals with a sample standard deviation, we want to also have a large sample size. That way we get something that's more similar to our normal curve. So we have two ways to find the area under the curve for our T distribution. So it's not exactly normal CDF. It is going to be something a little bit different. There is a table, but we're going to work off of our TCDF function in the calculator because our calculator does have a function where we can find the areas. So this is just a little snippet of what the T distribution critical values looks like. you've got your degrees of freedom in your one column, and across the top is your tail probability, or your area at one side of the interval. So we're going to talk about how to now calculate our t-critical value using our calculator. So not only do you need to know what confidence level you're working with, you also need to know your sample size n. So for example, if I'm trying to find a 90% confidence interval for a sample size of 30, I'm trying to find my t-critical value. I have my curve, and just like it was before, you're going to have a negative t-critical value and a positive one. The 90% area is in the middle. This is our 90%. And then above and below that, we split the remaining 10% in half. So 5% would be above and 5% would be below. Now, instead of using INV norm to find our t-critical value, we use something called INVT. So you still go to second vars, and it should be directly below INV norm. The area is going to be 0.05, and our degrees of freedom is our sample size minus 1, so 29. And then I hit enter, and again, we'll make it positive because, again, the plus or minus will take into the negative. So my t-critical value is 1.699. I'm not going to draw the picture for the rest of these. I'm just going to talk about how we plug into the calculator. So if I want to do a 95% confidence interval and my sample size is 20, I go to INVT. My area is going to be 0.025 because I take the 5% and divide by 2. My degrees of freedom are going to be 19, and we're going to get 2.093. So let's go ahead and look at both two examples with a 96% confidence interval, but with two different sample sizes. So you can see how the critical value changes based on the different sample sizes. So we'll do INVT. The area is going to be 0.02 because you have your 4% that you split in half, and degrees of freedom are going to be 229. And it's going to give us 2.066. Whereas if instead I had a very small sample size of 5, so I have INVT, area is still 0.02, but now my degrees of freedom are 4. It drastically increases our critical value to 2.999. So you can see that the smaller your sample size, the larger your critical value is going to be, even if you have the same level of confidence. So let's talk about how we do the confidence interval if we don't know our population standard deviation. So if we're based on knowing our sample standard deviation. So our conditions are still the same for random and independent. So I either have to have random assignment, which happens in an experiment, or you have to have random selection. So that's either an SRS or it says randomly sampled, somewhere like that. When it comes to normal, it's the same conditions as before. If your sample size is less than 30, you have to make sure your original sample is normally distributed. Which one way we can do that is to look at a graph of this sample data. The other one is obviously if your sample size is greater than 30, then the original population doesn't necessarily need to be normally distributed. And then for independent, if you're doing an experiment, individual observations are independent, so we can really just assume independence there. But if you're sampling without replacement, then you have to check your 10% condition. Your sample size n is less than or equal to 10% of your population. So once you have met all of the conditions, then you will decide between a one sample t interval or a one sample z interval. So the one sample t interval is going to be x bar plus or minus our t critical value times our sample standard deviation over the square root of n. So this is for sample standard deviation. And then we've already talked about our one sample z interval for means. That's x bar plus or minus our z critical value times our population standard deviation over the square root of n. So population standard deviation. It's basically the same formula. It's still your statistic plus or minus your critical value times your standard deviation. It's just, do you have a z critical value or a t critical value based on whether or not you have a population or a sample standard deviation. So let's go ahead and do a couple examples. So in our first example, we have that a sample of 45 new teachers found their average first-year salary to be $35,675. If the population standard deviation for new teacher salaries is known to be $2,548, find the 90% confidence interval for new teacher salaries and explain what this interval represents. So the first thing I want to do is determine whether or not I'm going to be doing a t or a z interval. And in this case, it says that I have a population standard deviation. So that means I'm going to have a z critical value. So I'm going to be using INV norm. And then my area is going to be 0.05. And I'm going to get 1.645 as my z critical value. Now I want to check my conditions. So for random, it doesn't specify that it's a random sample of 45 new teachers, but we'll just go ahead and assume that the sample we took is random. So remember, you are allowed to assume if it says sample that it is a random sample. For independent, 45 has to be less than or equal to 10% of all new teachers. And we'll go ahead and assume there's at least 450 of those each year. And then lastly, for normal, 45 is greater than or equal to 30. So now I'm going to go ahead and plug everything into my formula. So I start with my mean, 35,675, plus or minus my critical value, 1.645, times my population standard deviation, 2548, over the square root of n, which is 45. So I do 1.645 times 2548 over the square root of 45. We're going to end up with 35,675 plus or minus 624.83. Now, because this problem does talk about money, I will definitely round 2 decimal places, and that is the most decimal places you will round here, and it is mandatory that you round 2 decimal places. So when I add and subtract the 624.83, we end up with 35,050.17, and then 36,299.83. So for my sentence, we are 90% confident that the true average first year teacher salary is between, and then units for money is $, so 35,050.17 and $36,299.83. All right. Last example. We have, for a group of 35 random men subjected to a stressful situation, the mean number of heartbeats per minute of the sample was 126 and the standard deviation was 4. Find the 95% confidence interval of the true mean. So in this case, anytime in a single sentence they represent the mean for the sample and the standard deviation, that's going to indicate that you're looking at a t-distribution. So you're going to have a sample standard deviation. If it does not explicitly say the words population standard deviation, it's going to be a sample standard deviation, which means I have a t critical value. So we go to INVT. Our area is going to be 0.025, and our degrees of freedom is going to be 34. So when I plugged it in the calculator, we get 2.032. Now I'm going to check my conditions. So for random, it does say we took a random sample. For independent, 35 has to be less than or equal to 10% of all men, which there's at least 350 of those. And for normal, 35 is greater than or equal to 30. Now I'm going to plug in my information into my t interval. So we start out with our mean, 126 plus or minus our t critical value, 2.032, times our sample standard deviation, 4, over the square root of n, which is 35. So 2.032 times 4 over the square root of 35 becomes 126 plus or minus 1.374, which once I add and subtract is 124.626 to 127.374. So for my sentence, we are 95% confident that the true mean number of heartbeats is between 124.6 and 127.4. In this case, you can round one decimal place for our sentence, and then also there's not really so it would be 120, the units here would be heartbeats per minute. So let me know if you have any questions on how to calculate a confidence interval for a mean, whether or not that's with a known population standard deviation, or if it is with the sample standard deviation and you have to calculate a t critical value.